From directly overhead, an aircraft carrier flight deck has something off about it immediately. The landing runway doesn't run straight toward the bow. It's tilted, angled about 8 degrees to the left, pointing out over open water. It looks like someone made a catastrophic mistake in the blueprints, a design error that somehow slipped past inspection and got welded into a $13 billion warship. It's not a mistake. It's one of the most important engineering decisions in the history of naval aviation, and it directly saved hundreds of lives. Today we're going behind the design choices that make the U.S. Navy's most powerful machines look completely wrong at first glance. A flight deck that appears to waste half its surface. A submarine that manufactures breathable air from the ocean itself, 400 feet down, with no connection to the world above. And a $13 billion carrier that threw out a system with a 99.5% operational record and replaced it with something nobody had ever put to sea before. Every one of these looks like a mistake. Every one of them is exactly right. Here's why. It's 1952, and the Navy is facing a quiet crisis. The jet age has arrived, and it threatens to make the aircraft carrier obsolete, not through enemy action, but through physics. Jets land far faster than propeller planes, sometimes 40 to 50 knots faster. On a straight-deck carrier, a pilot who missed the arresting wire was heading straight into a wall of parked aircraft, loaded ordnance, and aviation fuel at full throttle. Captain Wally Schirra, naval aviator, test pilot, and later one of the original Mercury astronauts, summed up the era in a single line. In those days, you either made an arrested landing or you had a major accident. The American instinct was to build longer ships, more runway, more distance between the wire and the bow. The problem got bigger, and the proposed solution got bigger to match. A British naval captain named Dennis Campbell suggested something different. What if the landing strip wasn't aligned with the ship at all? What if you angled it, tilted the entire landing area off to one side, away from everything else on the deck? The objection was obvious. You're throwing away usable surface. You're carving into a deck that's already too small. A straight deck uses every square foot. An angled deck takes a chunk of prime real estate and aims it at empty ocean. That objection was completely wrong. The angle does something specific. By canting the landing zone roughly 8 degrees off the center line, it physically separates that zone from everything else on the ship. Aircraft staged to launch from the bow sit entirely clear of the approach path. Fueling points, maintenance crews, parked planes, all of it is off to the side, out of the landing lane. But the real breakthrough isn't the separation. It's what the angle does to a failed landing, what aviators call a bolter. A bolter happens when an aircraft's tail hook misses all the arresting wires. On a straight deck, that's a catastrophe in motion. The aircraft, still doing over 100 knots, has nowhere to go but into the barrier nets, or past them into the parked aircraft forward. Navy testing of the era flatly described the alternative to a clean landing as a barrier crash, which in plain terms meant a wrecked aircraft, a pilot in danger, and a flight deck out of action. On an angled deck, a bolter is a non-event. The pilot simply pushes the throttles to full power, rolls down the angled runway, lifts off over open water, and circles around to try again. No barrier, no wreckage, no fire. Even better, while one aircraft is recovering on the angle, another can be launching off the bow at the same moment. 2 operations running at once, neither one in the other's way. In late 1952, the carrier USS Antietam became the first ship to test the idea with real arrested landings, flying hundreds of approaches by day and by night. The results were so decisive that the entire American carrier fleet was redesigned around it. Every United States supercarrier since, every Nimitz, Every Ford-class ship operating in the Pacific or the Persian Gulf today uses a version of that same angled deck. One idea that looked like wasted space rewrote naval aviation. Would you have approved it, looking at those first blueprints? Most of the Navy's own admirals didn't want to. The second secret lies 400 feet beneath that surface. A nuclear submarine is on patrol. It's been submerged for 2 months straight. Inside the pressure hull, somewhere around 130 crew members are breathing, sleeping, working, exercising, every one of them steadily consuming oxygen and breathing out carbon dioxide. The submarine carries no tanks remotely large enough to supply that for months. There's no hose to the surface, no pipeline, no connection to the atmosphere above it at all, and it doesn't need one, because the submarine makes its own air. To anyone hearing this for the first time, the obvious question is where the oxygen comes from. The answer, that the ocean itself supplies it, sounds like science fiction. But it's been routine aboard American nuclear submarines since the late 1950s. The primary system is an oxygen generator that runs on a process called electrolysis, passing an electric current through water to split each molecule into oxygen and hydrogen. A nuclear submarine has effectively unlimited electricity, far more than it needs to move and operate the ship, and that surplus runs the generator. But you can't feed it raw seawater. Seawater is full of dissolved salt, and running current through salt water doesn't give you clean oxygen. It produces chlorine gas, which is poisonous even in small amounts. So the process begins one step earlier. The submarine first forces seawater through reverse osmosis membranes, the same technology behind large desalination plants. Under high pressure, water is pushed through filters so fine that the salt can't follow. The leftover brine goes back into the sea, and what remains is essentially pure water. That purified water feeds the electrolysis unit, where the current splits it, oxygen on one side, hydrogen on the other. The oxygen is monitored by an automatic system and fed into the ship's ventilation for the crew to breathe. The hydrogen, which is flammable and useless inside a sealed boat, is safely pumped overboard. But oxygen is only half the job. A submarine that perfectly replaced its oxygen but ignored carbon dioxide would still kill its crew, because rising carbon dioxide becomes dangerous long before oxygen runs short. So the boat runs chemical scrubbers in parallel. The US Navy has used a substance called monoethanolamine, MEA, for this purpose since the earliest nuclear submarines. The trick is elegant. Cool MEA chemically grabs carbon dioxide out of the air, and when that same MEA is heated, it lets the carbon dioxide go again. The captured carbon dioxide is compressed and pushed out into the sea, and the MEA is cooled and reused over and over. A separate monitoring system watches every compartment continuously for humidity, contaminants, and trace gases. And if the main oxygen generator fails or goes down for maintenance, the backup sounds almost like a contradiction. The crew burns candles. Not wax candles, but chlorit candles, sealed cylinders of sodium chlorate and iron powder that, once lit, release a steady stream of oxygen as they burn. The fire creates the very oxygen that keeps people breathing. It is, quite literally, lighting a fire to stay alive inside a sealed steel tube deep underwater. And the chemistry is exact enough that the US Navy has trusted it as an emergency supply for decades. Add all of it together, the reverse osmosis, the electrolysis, the scrubbers, the monitoring, the chlorate backups, and you get a submarine that can stay submerged for months at a stretch. Not because it carries enough air, but because it manufactures air without pause from the ocean pressing in on every side. On a modern nuclear submarine, the thing that finally forces it back to port usually isn't oxygen at all. It's running out of food. The third secret sits back on the surface. And it's the strangest decision of the three. If the engineering behind these machines is the kind of thing worth understanding, subscribing keeps more of it coming. There is a rule that holds across engineering, business, and especially military procurement. If it is not broken, do not fix it. And the steam catapult, the system that has flung aircraft off American carrier decks since the 1950s, is very much not broken. It is one of the most reliable pieces of machinery in the entire fleet. Carriers fitted with 4 steam catapults have kept at least one of them working about 99.5% of the time across decades of operations and tens of thousands of launches. It is not an antique. It is a proven, battle-tested workhorse. So when the Navy decided to scrap it entirely on the USS Gerald R. Ford, the lead ship of a new class, with a price tag around $13 billion, the reaction was the same as the one that greeted that angled flight deck. Why would anyone do that? And when the new system ran into technical trouble during testing, and even the president weighed in, complaining publicly that the Navy should go back to what he called goddamn steam, plenty of people felt the question had already answered itself. The replacement is called EMALS, the Electromagnetic Aircraft Launch System, built by General Atomics. A steam catapult builds up pressure and releases it in a burst to drive a piston down the deck. EMALS instead uses a linear induction motor, an electric motor that does not spin, but generates a moving magnetic field that races down a straight track beneath the deck, dragging a shuttle and the aircraft attached to it from a standstill to flying speed in about 2 seconds. From the flight deck, the launch looks identical. Underneath, the mechanism is nothing alike. The case against EMALS was simple. Steam worked, EMALS cost more, and it stumbled early. Why trade a system that fails once in 200 launches for one still working out its problems? But the case for EMALS was never about today. It was about what a carrier has to do over the next 30 years. A steam catapult has one stubborn flaw. It cannot fine-tune how hard it hits. The launch comes as a sharp, sudden jolt, stressing the airframe at the worst possible moment. For today's heavy aircraft, the airframes are built to take it. But the punch cannot be dialed down, and a catapult tuned to throw a 70,000-pound fighter into the air would tear a light drone apart. The Navy's entire future air wing is being built around unmanned aircraft, and the Navy's own program office describes EMALS, the Electromagnetic Aircraft Launch System, as designed to launch everything from the lightest unmanned aircraft to the heaviest strike fighters. Steam cannot span that range. EMALS can because its electromagnetic pulse can be tuned to each aircraft's weight, giving unmatched precision. There is a second reason that goes beyond aircraft. The Ford class was built from the keel up as a floating power plant, generating roughly 3 times the electrical capacity of the older Nimitz carriers. EMALS plugs straight into that electrical architecture, sharing the same power that feeds the ship's advanced radar, future-directed energy weapons, and next-generation systems still in development. A steam catapult would demand its own separate world of boilers, steam lines, and pressure vessels. Competing for space and energy, the new design was never meant to give up. This electrical integration is a major source of the ship's power. The payoff shows up in the numbers. The Ford's combination of electrical power and EMALS is built to push out roughly 30% more aircraft launches per day than a Nimitz carrier could manage. More combat power generated by a crew several hundred sailors smaller. Over a 50-year service life, the Navy estimates the new design saves billions of dollars per ship in operating costs. Those savings add up, and they matter. The new design saves money for decades. The steam catapult was not broken. Emails is not a repair. It is a foundation for drones, for energy weapons, for a carrier still fighting effectively in 2050 with aircraft and weapons that have not been invented yet. What looked like throwing away a system that worked was really building a bridge to a future the old system was never designed to reach. And that's the thread running through all three of these. The angled deck didn't waste space. It created the ability to keep flying when a landing went wrong. The submarine doesn't carry its air, it builds it, molecule by molecule from the sea around it. Emails didn't abandon a working catapult out of arrogance. It laid the groundwork for capabilities that don't exist yet. Every time the Navy builds something that looks wrong, there's almost always a reason hiding underneath, a problem the obvious answer couldn't solve. So which of these felt the most counterintuitive, and what Navy design should get broken down next? The comments are open, and the list of strange but brilliant engineering is a long way from finished.